Because in the keynote it was said that we should go to talks where we have no clue what the title or the description of the talk means. So I thought I can use that as an excuse to do the herald job for this sir. And this guy will talk about reverse engineering of chips, of ICs, integrated circuits, in a non-destructive but rather complex way of doing electrically stuff that's not in the data sheets, rather randomly at times. The priest that should give us this introduction into this type of voodoo magic is, let's be excited about Excite!
All right, so thanks everyone for coming out here. So, title of this talk is Glitching for Noobs, a journey to coax out chips' inner secrets. So basically this is kind of, over the last couple years, I've got interested in the topic of glitching and have been trying a whole bunch of different experiments and trying to learn for myself what it was all about. So this will kind of be a chronological kind of summary of what I've been up to in the last couple of years and what my findings have been. So just the quick agenda for the talk, quick intro, background, which is kind of the classroom learning about what glitching is, platforms, which is some of the various hardware platforms I've come up with in the last couple of years. Some of them were epic failures, some of them were actually seemed to work, so it'll be an explanation of the pros and cons. Example will be a real-world example of a secure microcontroller where I was able to basically get some glitching results out of, and maybe some food for thought, some thoughts that you guys could carry forward and how you could approach some of your own chips, and then finally any Q&A section. So intro about me, I'm an IT monkey or a consultant by day, and I'd consider myself a hardware hacker by night. So some of my interests are designing and reversing embedded systems, IC security and failure analysis, arcade platforms, and automotive stuff. Anything electrical or mechanical or whatever is pretty cool to me. And my contact info you can see there is just my xide31337 at yahoo.com email. So let's go into the background section, the classroom section. So what is glitching? So a glitch, and this is not necessarily electrical right now, the definition would be a transient which can induce alteration in a device operation. So a glitch is something that can mess up a device's normal operation. For this talk, we'll talk about electrical glitching specifically, and specifically clock glitching and voltage or power glitching. And there are other variants like laser, thermal, radioactive, but I'm not enough an expert in those topics to give them a good speech. So if we focus on the right-hand side there on non-invasive, semi-invasive, and invasive types, so electrical glitching would be considered a form of non-invasive attack on a device. So this doesn't permanently alter the device's package, the physical epoxy black part of the chip. It doesn't permanently alter operation of the device, so when you remove the glitching stimulus or you stop glitching, it should work normally again. And it's repeatable, which means you can start glitching, stop, go away for a little while, come back and do it again, and it's not going to harm the device, and you can keep repeating it. It's also surreptitious, which means there's no milling or drilling or etching or things of that nature, so it shouldn't look like you actually did anything to the chip physically. It should just look like normal. And another characteristic that's fairly important is that non-invasive attacks are usually cheap, so you don't need an expensive lab, and you usually don't need things like specialized microscopes or other expensive tools. And the kind of drawback to the non-invasive attack is that any background details you have beforehand are very helpful because they'll help to narrow the scope and what strategy you want to do when you're trying to glitch, rather than a completely black box device where you have no idea where to start. You could take many wrong turns, so any information you have beforehand would be quite helpful. So some examples of non-invasive attacks in the umbrella, there's 3 umbrellas, so there'd be fault injection, which would include clock glitching, voltage glitching. You can do thermal glitching, which is kind of where you're trying to affect the junction temperature of transistors. So, but really from a non-invasive standpoint, you're either trying to heat up an individual pin or try and heat up the whole chip package all at once, and it's not really precise. So I'm not sure if a lot of beneficial effects could come from the thermal side. There's also radioactive glitching. So if you just happen to have a source of X-rays, gamma rays, alpha particles, or neutrons walking around in your pocket, you may be able to sit those nearby the chip and get it to flip bits of memory or cause the CPU's instruction to cause the CPU to latch an invalid instruction or something like that. So the next umbrella is kind of side channels. So that's where there's power analysis, where you're basically studying the current consumption or power consumption of the chip, which can leak operations being performed, can reveal things like crypto round keys or kind of intermediate keys that could be used to derive like a full break on the encryption. And it can also indicate where the CPU is, provide an indicator where the CPU is in its instruction execution of the overall program. So there's timing attacks, which is simply trying to exploit the fact that conditional branches, when you're checking for a password or something else, you might stop when you find the first incorrect character, and it'll stop a lot faster than if it went through all the correct characters. So you'd be able to exploit the difference in timing to know if your guess at a secret password is correct or not. Data remnants, that's pretty much kind of like your cold boot type attacks. Or if you do a reset or power up the device and it doesn't wipe its memory, then there might be secrets still in memory. And then finally, the third umbrella is software. So this could be simple code vulnerabilities. The authors of the secure device may not actually be that versed in secure coding practices. So there may be just vulnerabilities sitting around like buffer overflows, stack overflows, things like that. Brute forcing. So you could simply try brute forcing if the key strength is small enough. The secret that gains you access to restricted memory areas, code protection. You might try brute forcing a crypto key, but if it's a relatively modern implementation, it's probably not going to work for you. And then finally, backdoors, which could be undocumented instructions in the CPU core. Could be debug interfaces, JTAG, UARTs hanging off the device somewhere, I2C, SPI, stuff like that. So those can be some of the more low-hanging fruit, but may or may not be present. So the second major class of attack is semi-invasive. So this is where you are altering the package of the device. So you might decapsulate, so you might etch away the epoxy packaging of the chip, or you might mill the chip from the top or the bottom to gain a better access of the actual die sitting inside the chip package. It doesn't permanently alter the device operations, so again, you'll be able to apply or remove some sort of glitching stimulus to the chip, and when you're done glitching, it should operate normally. Again, it's repeatable, unless you're doing laser glitching where you leave the laser on too long and you burn up something that you didn't want to. It's more expensive, so now you may need things like lasers, microscopes, chemicals, a mill, and this class of attack may be beyond a single person's budget. So depends how well funded you are or not. And then this kind of attack can provide background details rather than require them. So you'll be able to help narrow the scope and strategy potentially for your non-invasive glitching attack. And get a basic floor plan of the chip, for example, if you've got an optical microscope or something like that. So some semi-invasive examples, glitching, you can still glitch semi-invasively. So now you've got access to the chip's surface in some way, so you can use things like laser, flash, like a camera flash, high-intensity light, and thermal glitching, where now you might be able to direct a source of heat at a more precise area, but it's still going to be probably pretty kind could be fairly unreliable, or you'll end up altering bits or transistor gates in a larger area. So another type of example is laser scanning. So you can do it with the device being unpowered or powered. And so when it's unpowered, you basically have an optical beam inducing a current flow in the chip, which will change the current signature, like the power consumption signature. And then if the device is powered on, your optical beam can cause a measurable voltage change in the output of the transistor. Or the bus that the transistor is connected to. So it may be possible to do things like read out memory bit at a time by watching the current consumption and then sweeping the beam across the different rows or columns of a memory, for example. And then finally, there's you can do imaging attacks where you either do from the front of the chip or the back of the chip, where you mill away the back material. You can do visible wavelengths versus infrared. And you can do things like using optical microscopes versus electron or ion beam-based workstations. And this will allow you to get the floor plan of the structures and features of the chip a lot more precisely. So things like ROM, RAM, flash, E2, configuration security fuses, things like that. So now the highest notch, the most complicated type of attack is the invasive attack. So this is where you not only have the decapsulation and milling of the semi-invasive, but now you also have die alteration itself. So the actual little chip part of the microchip, and you can render the device non-functional with this process. For example, if you're trying to image the device layer by layer, obviously you're etching away materials, so the device, once that layer is gone, it's gone for good. So you'll want to have many samples available so that you can image the device like that. However, if you don't want to do that, but you want to have access to the surface of the chip, for example, and depending if you've got access to an FIB workstation where the device input pins like voltage, ground, clock, etc. are outside the vacuum chamber or outside the chuck, you can actually power the device up and run it while you're making modifications to it. So, like I said, most of these techniques are one time, especially the delayering process, whereas the FIB workstation can allow you to create edits, undo edits, and so you can go back and forth. So this class of attack can be very costly. So whereas the decapsulation and the readouts of the imaging of the chip can be somewhat reasonable, the actual being able to edit the chip can be very prohibitive depending on if you have access to the equipment or kind of an hourly rate to get on the equipment. And then finally, this class of attack will pretty much provide you with complete background details. So you can use all the floor plan data. You can actually force certain transistors or buses, circuit nets on and off, and actually get a good idea of how the device operates. And then you can feed this information back into the semi-invasive and non-invasive attacks to make them a lot easier, because you know where on the chip to target. So, as I mentioned previously, so some examples of invasive are decapsulation, so taking the chip out of the package, delayering the actual die. You could do a memory readout, which if the circuit has ROM, for example, you'd need to get through all the layers, all the metal layers down to the very first metal layer, and then that's where the actual ROM transistors are formed. You can do circuit edits, so etching where you're removing material from the die in certain areas. Deposition where you're using something like platinum or tungsten to deposit conductive material on the surface, so you actually create a conductive path. Wire bonding, where you're actually taking a wire bonding machine and putting gold bonding wires from the die of the chip or from areas of the chip out to a larger, more human-friendly package, like a very large dip or something. A dip package where it's 2 rows of 10 or 20 pins or whatever, and then you can easily work with that. And then you can also purposely destroy traces or transistors at this point if they're causing some sort of functionality you don't want. And finally, you can do micro-probing. So when you've got really, really tiny, for example, tungsten needles, you can actually stick them down on the surface of the chip and either listen to what's going on, or if that, or drive a signal back into the core of the chip somewhere. So that kind of concludes the different classes of attacks and kind of from cheapest to most expensive. So back to electrical glitching. So how do you actually, where do you get started? How do you generate glitches? So when you're making these glitch pulses that you're sending into the chip, either on the clock lines or the power lines of the chip, here's 4 methods that I basically came up with, and some of you guys are probably really smart and can think of other ideas, but these are the ones that I could think of. Simple clock divider, phase lock loop. If your device in this example had an FPGA with a PLL, use that. Poly pulse width modulation, where you've got multiple PWM signals further apart from each other, and then polyphase, where you've got 3 signals that differ from each other in their phase. So the first clock divider example, this one's the simplest, where you literally take as many D flip-flops as you want, and every time you go through a D flip-flop, you basically divide the original input signal by 2 when you feed the output of the flip-flop back to the input. So you go from 48, divide by 2 down to 24, divide by 2 again down to 12. And so now what you do is you have this multiplexer where you feed it the slow 12 megahertz signal and the original system clock 48 megahertz signal, for example. And you run the device through most of its lifetime on the slow signal, and then you toggle the glitch select line down here at the moment you want to glitch, and then now all of a sudden you'll get some 48 megahertz pulse train instead of the slower 12 megahertz in this case. And you can use this directly as the clock signal to the input of the device, or you can use it to gate the switching of the voltage from a high value to a value that's known to cause the device issues. So it's flexible and can be used either way. So this is what the waveform would kind of look like. Let's say, here's a single speed clock and here's a double speed clock. And then when you bring your select line high which is the select line on this multiplexer down here, then all of a sudden you will switch the actual waveform that goes to the chip from the slow to the fast. So it simply just switches between slow and fast. So the second method is the phase lock loop, PLL. So the PLL uses integer multipliers and dividers to create a fraction, an integer fraction, something over something, that can be used to multiply up and then divide down to get you many more different kinds of clock speeds than simply dividing by 2 each time. So then this way, you'll get, for example, feed the PLL with this normal fast clock, and then instead of 24 and 12, you also get 16 and 4, or whatever combination of speeds you want in between. Combine all of those with the fast system clock, add a couple more select lines, and now you've just given yourself more choices in terms of what speeds you want to play around with. So if you do this work up front, then you don't have to keep changing your circuitry down the road. It's more flexible. So the third method is poly PWM. So this is where you use multiple pulse width modulation blocks to generate clock signals with successively longer and longer duty cycles. So now in this case, instead of changing the frequency, we just keep our system clock at 12, 12, 12, 12, all the way through these blocks, but now we have a 50% duty cycle, which means 50% duty cycle means half of the waveform, there's equal parts on and off in the cycle of a waveform. So you'll see in the picture, 70% means that the waveform is on 70% of the time, off 30% of the time, so the remainder between 170 and 100%. And then the third one is 85%. And then what you do is you feed these into a XOR gate, and then the output of that, couple it with one more XOR, so it's basically like you're XORing the 2 signals and then XORing in the third signal with it. And then that'll get you a glitch pulse, and then again, you just take your select line to go between the original clock and then the shorter pulse. And here's kind of how the short pulse gets generated. So again, the frequency is the same and the phase is fixed. So these things are locked to. If you look here, right in the middle, those lines all start at the same time. So the phase they're all locked with each other. However, when you change the duty cycle, you'll see that the 60% wave is on a little bit longer than the 50%, and the 70% is longer than both of them. And it's like a staircase effect. And so what happens is, when you run these through those two XOR gates, the difference between the first and the second pulse gives you when you want the pulse to start. So that's right, this left side of it right here is when you want it to start in horizontal relation to the on part of the pulse. And then this third duty cycle wave, the difference between the third and the second, so the 70% and the 60%, gives you how long you want the actual glitch pulse to last for, or how long you want it on for. So this is actually a pretty flexible method, and you don't need PLL hardware in your device if you want to be able to generate these waveforms. And so basically, you get one pulse of it, whereas the fourth method that I can think of was polyphase, so multi-phase. And this is where you generate multiple waveforms, but each one is phase shifted from the previous waveform by so many of degrees. So the frequency is the same, 12 megahertz, 12, 12, 12, so it's all 12. But now you're shifting the actual relation of the second and third waves to the first wave. And again, selecting when you want normal clock versus glitch clock. So now the only real difference is now the on-time duration, for example, right here is the same in all three waves. So it's not differing like last time, but the waves are offset. Their beginning, when they start, is further and further ahead from each other. And effectively what it does is it gives you a glitch pulse on the beginning edge, and the trailing the end edge of the waveform. So you get twice the many pulses as you did with the poly PWM. So do you need it or not? It all depends on your application. It may help you to be able to generate them more quickly or more often, but it's just another way to do that. So a quick aside, like I'm using Altera FPGAs, so you don't have to worry about reading all this big paragraph. This was just an excerpt out of Altera's manual on, for example, and Xilinx will be similar. If the FPGA has a hardware PLL, how you're able to, these are the steps, how to instruct the PLL to actually create phase shifts from its different PLL outputs, which is basically how I took those different phase shifted outputs and created these waveforms. So then it's got this specific timing diagram where you're supposed to give it these, whether you want to step at 1 or more degrees, whether you want to step forwards or backwards, and phase done is just what the PLL module outputs back to you when it's done shifting. So this was looking kind of complicated to get all these timings right, because the FPGA I was using had a soft CPU in it. So I ended up having to make a state machine because my soft CPU was so slow in relation to the PLL's ability to shift its phase that I would say, go shift by what I think is 1 degree, and it would come back with like 7 or 8 degrees of shift, which to be scientific about it, I wanted to go 1 degree at a time so I could see the effects with each degree of shift. So I just made a simple state machine that just literally, when the CPU says, I want you to shift 1 degree, it goes off, programs the PLL, and then it exits the state machine and waits. And the CPU will still have said, I want you to shift 1 degree, and it'll be stuck in the start equals 1 position. Then finally, like many, many clock cycles later, when the CPU, because it's much slower than this PLL, when it finally responds, then you can tell it to put the start bit to 0, and then it'll bring you back to the initial. So this way allows you to shift 1 degree at a time, so it'll get trapped in this loop until your CPU is actually able to shift. So back to the classroom. So what is clock glitching actually doing? So basically it's a momentary burst in frequency, as you could see with those little pulses compared to the normal clock pulse. All of a sudden you had a quick one, usually greater than the max frequency of the device. So simple case is if you've got a datasheet, look it up, see what the device is rated to run at, and then go even faster or many multiples faster. The glitching is timing critical, so the value of the program counter, so where the program is in its overall execution, where the CPU is in its overall execution of its program, you need to know if at the specific point you think it's going to be doing a compare, or you know it's doing a compare, you want it to land there. And then now you know that it's doing a compare. Where in the actual compare instruction do you want the glitch to hit? So that's your offset of the glitch within a single instruction. And then finally, how long do you want that pulse to last, which was kind of that third duty cycle or that third phase shift wave in those diagrams determined how long the actual pulse lasted for. So basically what this does is it causes registers inside the device or flip-flops to latch invalid data because signals are still propagating through combinatorial logic through the device when you suddenly clock it. And so basically the destination flip-flop, from the source to the destination as the signal's propagating, you clock it ahead of schedule. So the device will basically latch invalid data because the correct signal hasn't propagated its way towards the destination flip-flop yet. So what'll actually be happening is you'll either get instructions in the CPU core will either be duplicated or mutated. So what would happen with a duplication is, let's say the real program had a compare and then followed by a jump. So it's checking some condition in an if statement and then jumping. What you'll actually get is the compare will become compare. So that jump will actually go away, and that's usually caused by a fault in the fetch stage of instruction processing. So you've got usually fetch, decode, execute, memory operations, and register write back are typically your 4 or 5 stages of your RISC CPU, for example. So it'll mess up the very first fetch stage. The next is mutation, and this is where you actually turn like a jump instruction into an add, which is probably harmless in this case. It gets you what you want. It bypasses an error check, for example, but it just turns it into an add. And usually in the fetch, decode, execution steps, it's the actual execution stage that gets messed up when instruction is mutated. So the actual core is about to execute an instruction and then it gets mutated into something else. So this is kind of the hardware equivalent of patching a software binary, where you go into your hex editor, edit an instruction to become something harmless. And so kind of technically the instruction is not actually skipped. So the program counter or the instruction pointer on the CPU doesn't just skip ahead to 2 memory locations to the next instruction. It's still executed. It's either going to become a duplication or a mutation. So it'll feel like it's being skipped, though, in those cases. So sometimes this quick burst of clock frequency can affect your config or security fuses. So they'll either fail to set in some cases, or they're set incorrectly. So this could actually be kind of helpful to wipe out some certain code protect fuses or things like that. But it's a lot more particular in how it works, depending on the device. So here's kind of an overview of that phenomenon where you have the source flip-flop and the destination flip-flop, then you've got a bunch of combinatorial, like individual and, or, et cetera, gates through the middle. And what you're doing is you have a clock event, so now all of a sudden you have your glitch pulse, and this pulse occurs down here well before it was expected over on the right-hand side, which coincides with where the actual destination flip-flop is in time and propagation distance. So you clock it way ahead of schedule, and now it'll clock in some garbage data here rather than the proper signal making its way all the way through. So that was clock glitching. So what's the mechanism of voltage glitching? So this is a momentary reduction in supply voltage to the device. So what you do is you drop the voltage to or below the transistor's switching threshold. And a rule of thumb is try supply voltage divided by 2 and start from there. It could be lower, it could be higher, but it's a good starting point. So what this does is this increases the propagation delay, which is literally the delay of the signal propagating through the device. So it gives you kind of the same end effect. And why that happens is because when you decrease the supply voltage, it decreases the drive strength of the transistors, and this lower drive strength will cause slower rise time. So you'll actually, instead of a sharp edge rate, a sharp transition of a signal transitioning, you'll actually get it'll take a long time to plateau and a long time to discharge, basically. So that gives you that effect where it slows that propagation of the signal down. And again, just like clock glitching, you want to be accurate to where the instruction is in the overall program. where inside the particular instruction you want, the offset of the glitch, and then how long you want it to be active for. So what it's doing is it's also altering the values at the memory sense amplifiers for flash, E2, RAM, etc. And so this has the effect of corrupting data latched onto the address or data bus. So you can actually have the program swing off wildly to an invalid location because you latch a bad value onto the address bus. Most cases it'll crash the chip, but in some cases it might jump you into an area that the program was never supposed to reach. So, and again, security fuse logic in the voltage glitching mode can also latch corrupt values due to that effect where you're right at the switching threshold of the transistors. So just to dispel a few misconceptions, I don't recommend throwing random voltage sags and surges at the IC and seeing what happens. I would recommend respecting the absolute maximum VCC and VCC for the I/O pin ratings on the datasheet if you have one. Otherwise, you can have latch-up occur, which is basically kind of a short between the power rails of a device or two pins of an IC. And this can cause the device to overheat or basically destruct due to overcurrent, so you want to avoid latch-up. Some 74 series logic, you can give it very high and low voltage swings on the input pins, but usually they have a current-limited condition in the datasheet, like specific Fairchild chips, for example, but not National Semiconductor will say you can do this. And that's because you have to put a giant current limiting resistor in front of the pin, basically. So don't throw these crazy high or low voltages at a chip unless you got a bunch of them, basically. And you're not randomly jarring the clock frequency to a wild extent. You're specifically targeting that pulse at a certain point. And you're not technically skipping instructions. As I said, you're kind of duplicating or mutating them. Again, it's timing critical. And finally, unless the chip is stuck in a loop, just randomly glitching like with random voltages or the clock at certain offsets randomly is usually going to be counterproductive unless the device is stuck in a tight loop with a few instructions. Then obviously the search space that your glitch has to hit is very constrained, it's very small, and it's more likely you can pop out of the loop. So what are some of the outcomes in general that voltage or clock glitching or potentially any glitching can provide for you? So you can make the CPU replace impeding instructions, so you turn that compare jump into a compare, which doesn't jump anymore. You can truncate cryptographic operations or keys, so reduce the number of rounds in a crypto encryption or decryption process. You can do linear code extraction, where you basically you walk the address space of the device, address location 1, 2, 3, 4, all the way until the memory map loops, dumping out the data from the device byte by byte. However, you do usually need an I/O channel to actually get the data out, so a UART pin or something of that nature. You can do things like bypass bootloader enforced checks, so you can stop the memory management unit or page tables from initializing if they're mapping in sections of memory over top of the bootloader to hide it or conceal it or just to save, to provide more space. You can stop that from happening. In some cases, you can prevent lockout counters from rolling. So if it's a secure crypto memory or something like that, where you only have so many tries before you're locked out of the device, if you glitch when it's recording or decrementing your try counter, the number of tries will never change. So you can just keep doing your malicious activity over and over again without the device finally reaching zero and then erasing itself or halting or something of that nature. And then finally, in some cases, you can erase security fuses or lock bits. So what this will do is keep the flash and E2 intact, so then you can just take the device off the board, for example, plug it into a parallel or serial programmer and just read out the device that way. So if you're looking at chips to try some of this stuff on, there's pretty much your general purpose and your security enhanced categories. So things like general purpose things like CPUs, microcontrollers, memories, digital signal processors. And then on the security enhanced side, you've got things like SIM cards, smart meters, military devices, chip and pin, pay TV, transit or metro, and then automotive devices. However, the security enhanced side is, I'm not saying like stuff's going to work necessarily there. It depends on the age of the device and how smart the developers were when they made it. A lot of these security enhanced devices are actually really, really good. So things I don't recommend is trying to trying to attack like FPGAs or ASICs simply because there's so many unknown variables, and unless you know there's a certain CPU core inside that ASIC or that they've programmed a certain block of logic in the FPGA, it's you'd be fishing around in the dark basically. So what are some countermeasures that, for example, a manufacturer, or if you're writing code or embedded code for a device, what could you do as a countermeasure? You could use a CPU which halts or traps on invalid instructions. However, in the case of the instruction mutation where your jump became an add, the add instruction is still a valid instruction in the table of instructions in that device, so that may not even trigger an invalid instruction fault. So better than nothing though. You could erase volatile memory on startup or reset, just no matter what, as soon as the device comes up, just a good best practice to wipe the memory. So what you want to do is minimize the number of copies of important secrets or primitives. So like for RSA, P and Q, or any combination of those intermediate values that could derive back to your private key. Keep as few of those as possible, and obviously wipe them between iterations of a routine in certain parts of the program if you don't need them. If you don't need them, get rid of them. So clocking, when you're clocking the device, you could use a device that runs off an internal oscillator. So it just ignores the clock pin from the outside world. So that pretty much would cut off any clock glitching attacks. You could use asynchronous logic wherever you could. So if something didn't need to be clocked by a clock signal, then don't. And finally, you could use aperiodic or random clock period generation, which is where the actual clock period is changing between cycles, so it's unpredictable in terms of the timing. Finally, you could use obscurity, which is another kind of last layer of defense. It's not a prime defense, but use a really complicated, 48-bit, very long instruction word DSP core with poor documentation in your product. It'd probably make it harder for you to write if you're the developer as well, so it's not that great of a countermeasure. Finally, so supply voltage, use glitch or brownout detection, and this can be very complicated with fast transient detection that actually detects and responds. You could use a simple low-pass filter which simply ignores and erases that quick transient as far as the chip's concerned, so it doesn't even see it. Or you could be more aggressive and reset, halt, or wipe the device if you detect someone is trying to mess with your chip this way. So many general purpose devices have little or no design and protection. So these are chips that you guys could look at in terms of interesting targets. So AVR's PICs, TI MSP, for example, they do have code protection. So it may not be your first choice if you're just starting out or learning. And then at the extreme level, modern smart cards, chip cards have extensive protections. So they've got glitch detectors, they've got the random and aperiodic internal clock, which is changing in its length between cycles, and you'll have two CPU cores in lockstep that are sanity checking one another. So if some instruction goes wrong in one core, the other core will be offset and catch it and do something like either reset the device or erase the memory, etc. So this will detail some of the actual hardware platforms that I made over the last couple years that I use for voltage and clock glitching. So the summary of this, guys, basically this is an off-the-shelf Aero low-power reference platform board that I found for really cheap on eBay. Like I think it was between $20 and $50 US, so not crazy expensive. So it has an Altera Cyclone 3 FPGA, which I put a MIPS 32-bit soft CPU inside of it. That 3 PWM clock generator that I showed you before, the 3 polyphase, like the polyphase clock generator. It's got a regular 16550 UART. It's got some driver functionality for SRAM and flash control, and then some output multiplexers to switch between your low-speed normal signal and your high-speed glitch signal. And then this messy breadboard at the bottom is just doing voltage level shifting and signal conditioning and buffering, so that the end target in the FPGA, for example, doesn't get blown up by if the target device is running higher voltages than the FPGA. So this is a close-up where you've got kind of general purpose I/O pins up here. You got 3.3 volt supply, 5 volt supply, FT32 USB to UART chip, SD card, which I'm not using at the moment, but could probably be used for data logging. CPLD, which is just used to program the FPGA from a PC, the actual FPGA, Intel Flash, and then some Micron PSRAM, which is actually DRAM wrapped with a SRAM interface, so it's just easier to work with it. You don't need to have all the crazy DRAM timing signals exactly right. And then on the solidless breadboard, there's just some, these 74, the LV is important, so 125 is just a buffer that takes an input, a signal, provides an output, and then it's got beside each pair of those input-output pins, there's an output enable pin that lets you float the signal or drive it. And the LV is important because it's 5 volt tolerant, so you can power the device with 3.3, but it'll accept 5 volts as input. So any outputs from it will be 3.3, but let's say your device runs at 5 volts, it can output its signals to the input of this as 5, and then this will output them at 3.3 to the FPGA where you won't blow it up. Whereas if you drive the FPGA at 5, it won't last very long. So other than that, just your 5 and 3.3 volt power rails, and then just the pull-up pod I was playing with to strengthen the drive strength of the one of the signals. So here was another iteration, soldered breadboard, which was kind of a beefed up version of this that I thought would work at higher frequencies because it was soldered, but clearly you can see from this mess of wires that my routing is amazing. And so I use this board for both voltage and clock glitching, and it has what I call a ghetto DAC, which is basically you provide a PWM, so a varying duty cycle signal of how much on time to off time into a low pass filter, and the output of that low pass filter will actually be a steady 0 to 5 volt range DC voltage based on the pulse width of the signal coming in. So it's just an easy way for a microcontroller or FPGA to send a PWM signal, and you end up getting a varying voltage rather than having a real digital to analog chip that does that in its own way. So for a while, I seriously considered Arduino for about 7 minutes, because why not? And the problem with Arduino is the crystal is fixed on board wherever it is. Can't see it at the moment, but anyways, I think it's 16 megahertz. And as soon as you go and use any of the timer or output compare registers to divide that clock down, you can't take the 16 megahertz and provide it directly as 16 megahertz on an output pin. It automatically goes through a divide by 2 as soon as you turn any of those timers or compare features on. So already before I even started, all I could do was 8 megahertz signals out of this thing. And so if your device is running at 2 or 4 megahertz, that might be enough, but if your device is running at 32 megahertz, then obviously this isn't even going to help you. So it just wasn't flexible enough. So then I thought I'd make an even more feature-rich boards, and because I'm thrifty, decided to etch it myself, which was pretty much an epic failure. Because what happened was my transparency that you shine the fluorescent light through with your mask of the layout was slightly off the surface of the board, which had the effect of being out of focus. The artwork was out of focus. So basically I had blurred pads and traces that didn't develop properly, so you can see stuff like this probably isn't conducting too much current through it. Sections right here were wiped out entirely, and you can see the ground plane is starting to get attacked because you leave it in there to try and eat through some areas. Meanwhile, it's starting to eat through areas you want to stay there. Here's another kind of example of that. More failure. So then what I decided to do was break down and go to Osh Park and make a professional PCB, because as you can see, it required a few edits after the fact already. And so this board was primarily designed for voltage glitching. It has a ATtiny 2313 CPU that I just had lying around. And why it's not great for clock glitching is that it's obviously there's a fixed crystal on there, so you only have a certain range of divisions you can do with that. And it also, like the other board, uses the ghetto DAC, and this buffer simply strengthens the output drive current so that you can actually power the device up through this buffer rather than having a weak, 5, 10, 20 milliamp signal coming right off of one of these 74 series logic chips. So here is another device. My my sniffer board, which is just basically used as a man in the middle. So this would plug into the FPGA. And then this AHC125 is just like the 74LV125. So it's just a 5-volt tolerant chip that can drive signals at 3.3 volts to correct the voltage mismatch between the FPGA and the target. And so basically that allows for data logging. And then what you can also do for a cheap and dirty data logging and logic analysis is you can use this logic block called Altera Signal Tap 2 in the FPGA. And what this is a logic kind of a soft logic analyzer block that can analyze almost any signal, net, bus, external I/O pins, whatever you want. And you can save more and more samples by using up more logic elements or slices, if in Xilinx terminology, of the FPGA. So there's plenty of trigger options, from simple low, high, or edge triggering to you can chain events, do multiple segments of capture. So it's got all sorts of triggering that and storing that a full logic, a hardware logic analyzer would have. And then you can export the data in plain text images or other formats. So the plain text would be a comma-separated list of the signals over time, like 1010, and then you can pack that back into an actual, parse it back into a protocol. So it's equivalent. It's also called Xilinx chip scope if you're using the Xilinx product. So here's a quick summary of what you do. You basically pick the clock that you want to clock the logic analyzer at, pick which signals of interest you want and what logic levels or triggering you want the recording to kick in at, and then you get a nice waveform view where it shows you what those signals did after and before the trigger point, if you want. So let's roll into the last section, which is the example device I was playing with. So I had a victim IC. I knew it was a secure microcontroller, but I wasn't sure what the internal architecture was of the CPU core. I knew that it paired with a partner device, so a reader and then the target chip. So the reader would send data to the chip would encrypt or decrypt it with a key that was inside of it, and then send the data back to the reader, which would go off to the rest of the device. So I was basically starting with a black box, and so I wasn't sure what data sheets to look for, or even if the device was known, the data sheets might not have been public anyways. So what I did was basically start probing the pads of the chip, of the victim chip, did an initial sweep at the multimeter. I've got like a little fluke meter, so the little bar graph part of the meter will respond a lot faster than the actual numeric digits. And then I'd come back with an actual oscilloscope for any pads that showed interesting, quick-moving activity. So I found one pad appeared to speak a slowish serial protocol. So all I did was capture and just transcribe the beginning of that waveform because my scope had really small amount of memory, onboard memory. And it was only one pin doing that, so my guess was that it was some sort of half-duplex communication going back and forth because I knew the victim talked to the reader. So then I used that sniffer board to basically man in the middle of the conversation, and I used that signal tap logic analyzer software in the FPGA to export the waveforms as plain text, pack those individual bits back into bytes, read the byte string, and I found out that after Googling, that I had a ISO 7816 APDU header that I found. So at that point, this was good. So then what I was able to do is add a UART to the FPGA, and so that's 16550. So what this does was allow for hardware framing of the transmission and receive data with the victim. Otherwise, you don't need a UART. You can do it with bit banging, but then you have to waste like 2 or 3 days potentially to get the timing perfect. So it's just easier. And then with the Altera, you can use this logic block called JTAG UART to talk to the MIPS 32-bit soft CPU running in the FPGA, and then the CPU can talk to the victim. So then that way you just need one programming cable from the board to a USB port on your computer. You don't need a cable to the victim and a cable to the FPGA. So now that I had that kind of intermediate speaking going on, I had the PC speak ISO 7816 smart card protocol with the victim. And so the 7816 header has a length field. So I proposed a theory that the victim is probably comparing the length that you send it in the length field from the device or from the reader to the max that it'll allow as its buffer input. Usually, like, I'm not going to allow you any more than this because I've only set aside 64 bytes of RAM to store the commands, to RAM, for example. And if the length is if the length, my hunch was that if the length was too long, then issue an error. So then what I was able to do, the next theory was issued a whole bunch of too long commands to the victim, but otherwise corrected up the checksum so that it was correct, and then observed the error response from the CPU. And at this point, now is when you get ready to glitch. So this is what I call the sucker punch, this is a clock glitch where you see a quick pulse in time versus the normal, like this pulse wouldn't be here normally in the normal speed of the device. So you can do a 1-2 punch, which is simply 2 pulses one after another, and you can try any variation of this 1, 2, 3, 4, 5 different periods. So this is clock glitching, and glitching during the suspected victim's command handler. So where the victim would be accepting commands and checking the length on them, the length of the packet. So what I do is try different pulse offsets and durations to try and narrow down when it was executing, for example, the compare instruction that would be checking the length of the packet you're sending it. And so you know you've hit a milestone when the victim, instead of when you give it these packets that are very long, but with correct checksums, and it normally errors out, all of a sudden it doesn't error out, and it actually processes the command, even though it's got all these garbage bytes at the end of it to make it way longer. So now you know that you've probably hit the compare or the jump instruction with your glitch, and you've stopped the device from issuing an error. So at this point, if you're already sure, like there's usually Motorola 6805 based cores or Intel 8051 cores are the majority of smaller 8 or 16-bit embedded devices. So use that as your guess. You can, so as I said, you pad more and more data to the end of the command, and then wait till the victim crashes or does something weird. So you might, so as you're padding more and more data, eventually if it crashes, so now you've sent in a too long value, but you make it even more long. That's not good English, but whatever. So eventually you'll stack the smash, but it could be hard to notice if there's a hardware watchdog that notices that all of a sudden the CPU flew off into nowhere land and then reset it. But basically, that's what I was able to get to the point where I knew where the stack pointer was, gone beyond it, and wrote the return address. So now that you know where the return address is, you can actually start writing programs for this device because now you control the return address. So you can write a tiny little program that tries to write to low address special registers. So like Motorola 6800, for example, port, which is the output pin value, pin, which is the input pin, DDR, which is your data direction register. Start playing with those and see if you can get your I/O pin or one of the important pins on your victim to toggle all of a sudden change. Because now you know where the address, now you know that those pins exist and how they're mapped into memory. So here's your typical layout of the victim's memory space. But yeah, so your next milestone is where you do actually have the output pin chain, one of the pins on the device, either the I/O pin that you're talking to it on, or a different pin that might be bonded into the chip. If it changes value, now you've confirmed code execution. Your architecture guess is probably pretty good because you wrote a little program in that target architecture of a few bytes to write to that low area. And it's probably von Neumann or modified hardware, Harvard that lets you do that. So now you're getting really close. The next thing I did was write more code in that in the 6805 that loads a dummy ASCII byte like 5 or F or A or some value of where it's alternating bits into a register like, so A on the 6805, for example, then sweeps jumps into address space. So what that's doing is I'm searching for the serial transmit routine software, the address and software, because this thing, the victim bit banged the output, so it didn't have a hardware UART. It had to jump to a software address when it wanted to echo a byte back to me. So I just kept sweeping addresses in as that return address with the smash stack until I got my byte back that I sent in, and now I knew I found the serial transmit handler and software of the microcontroller. So now all you have to do is make a code loop that starts wherever you want, wherever the current execution is, or maybe it jumps to 0000, loads the data from 000, address 000 into a register, jumps to the serial transmit routine, which will echo that data byte out the serial port, increment the address pointer, and then keep going over and over again, moving to the next memory location. And you have to be prepared to empty the FPGA's receive UART buffer quickly and regularly, because basically the entire codes and data space in this particular chip will be dumped out in an endless loop. It'll just keep mirroring and wrapping over the address space, and this is kind of what's known as linear code extraction. So the summary, so now that you've got this whole dump of the code and data space, you can try and figure out the memory map if you're still not sure of it. Analyze the dump for any mirroring of the address space so you know where the overall dump starts repeating, because it's going to be in an endless loop, so eventually it's going to be a finite bounds of where the memory map is. Try poking values into certain memory locations, see if they change. If they are, you're probably dealing with RAM, or maybe E squared or flash, depending, but usually E squared and flash have more complicated write routines. And now you're back in familiar territory. So you can disassemble that code dump you have, or write a disassembler if you don't have one on hand. You can search for crypto secrets or keys in that dump, serial numbers, seed keys, whatever, and you can discover any code vulnerabilities that where it was just poor craftsmanship on the creator of the code, where you can just find vulns. So conclusions, electrical glitching can be a viable attack vector against a variety of ICs, except for security hardened, purpose-built security ICs. It can be cheap to perform. You don't need a big lab or expensive lab. It's usually non-destructive in nature, so it doesn't affect the device, and it's another tool in your arsenal when other approaches have failed. So that is everything, and I guess I'm not sure if we can get a couple questions or.
Yeah, I think we have some time for maybe 3 or 4 questions. If you have questions, please line up at the microphones down here. Up there are no microphones for questions. And while you pile up, we hear a question from the internet. Signal Angel.
Thank you. First question, how many chips do you destroy on average until you successfully break in?
Some devices where you only have one device, you have to be very careful with how you proceed. So in those ones, like I said, with the absolute maximum ratings of the device, you do not exceed them. You play it very safe. Other devices where it's a more general purpose microcontroller or whatever, where you got a whole tube of them, then you can throw 17 volts at a 5-volt chip or whatever you want. And in some cases, you'll blow up 10% of the devices like very quickly, but the other, you'll blow up 90% of your devices very quickly, but 10% of them might actually latch something advantageous and do something you want before they blow up.
Thanks. There is somebody at microphone 1. Please ask a short question.
Hi, I was just wondering how reproducible the glitches are. Like if you find a particular offset and length.
Once you find the offset, depending on the timing drift of your own hardware, that's pretty much the limitation. You will be able to hit that compare instruction every single time.
Will it nearly always do the same thing every time?
Usually, yeah. Like if it is a compare or a jump right after it from a conditional branch, it will stop the branch from happening or cause the branch to happen with very good repeatability other than the drift in your own clocking hardware.
Are there any more questions? Yes, microphone number 4, please.
Yes. Is it possible to glitch through a PLL? It's almost impossible.
Oh, to glitch an actual PLL device or one that's clocked behind a PLL?
Yes.
Ooh, that I haven't actually tried. I would assume it would be a good defense, but I can't comment too much more. I haven't actually tried specific hardened devices like that.
No more questions for now.